High-performance liquid chromatography relies on the molecular interactions between molecules to separate mixtures into their corresponding components. These components can further be analyzed in order to identify and quantify the parts within the mixture via a variety of detectors such as a mass spectrometer or a UV-Vis detector. The main components of a HPLC machine include a solvent reservoir, a high-pressure pump, an auto-injector, a HPLC column, and a detector. The solvent reservoir is where the mobile phase of the HPLC machine is stored. The mobile phase usually consists of a mixture of polar and organic solvents, usually mixed with water. The mobile phase can either be polar or non-polar. When it is polar, it is known as a reverse phase HPLC, and when the mobile phase is non-polar, it is known as a normal phase HPLC. Some common solvents used in these mobile phase mixtures include acetonitrile, ethanol, heptane, and propanol. The mobile phase can also have some acid or base added to it. This allows for acidic or alkaline analytes to be in an ionic state as it goes through the HPLC, which allows for greater resolution when using a mass spectrometer. The mobile phase can undergo two different extraction modes, the first being isocratic elution, where the proportion of solvents in the mobile phase remains consistent throughout the analysis, whereas the gradient elution mode has a computer varying the solvent proportions throughout the experiment. These modes allow for greater resolution of analyte peaks to be achieved. The high pressure pump is used to maintain a consistent rate of flow of the mobile phase throughout the HPLC system. This is the main force that drives the analytes throughout the system. This rate of flow can be changed in order to obtain optimal resolution of certain analyte peaks. Depending on the composition of the mobile phase, there will be an optimal flow rate which will offer the greatest resolution for that analyte. The auto-injector is a modern-day method used to replace the outdated method of having personnel inject the sample into the HPLC system. The latter method was prone to human error and failure, which would cause experiments to obtain incorrect results, whereas the auto-injector utilizes a robot to inject multiple samples into a system with a high reproducibility. Most auto-samplers can inject 1 microliter to 10 mils of a sample, with it being able to accept 100 sample vials at one time. The automation of the injection process also eliminates error, causing greater validity and confidence with the obtained results. The HPLC column is where the stationary phase resides, usually taking the form of small beads. Like the mobile phase, the stationary phase can be polar or nonpolar and will be the opposite polarity of the mobile phase. As the analyte travels through the column, it will either spend more time in the mobile phase or the stationary phase. This arises due to the different molecular interactions such as dipole-dipole interactions, van der Waals forces, and ion exchanges that occur between the phase molecules and the analyte molecules. Most columns consist of stainless steel tubing with packed silica beads. This configuration can change depending on the analyte undergoing analysis. For example, a separation of enantiomers in a racemic mixture requires a special chiral column that will allow this separation to occur. A UV-Vis detector or a mass spectrometer are commonly used as detectors in HPLC analysis. A UV-Vis detector utilizes a tungsten lamp to produce wavelengths of light within the ultraviolet region of the electromagnetic spectrum. Analytes will absorb this light at different wavelengths once it has been passed through the system, which allows for identification and quantification of the components, whereas a mass spectrometer relies on the analytes being in an ionic form, allowing for a magnetic to move the ions in a particular manner depending on their mass to charge ratio. This will create a spectrum based on the deflection of the ions and their corresponding mass to charge ratio. From this data, the ions can then be identified and quantified, which allows for both a qualitative and quantitative analysis of the sample. A mass spectrometer is more sensitive, selective, and reliable than a UV-Vis detector, making it the ideal detector for HPLC. HPLC is usually reserved for the analysis of organic compounds, organic ions, chiral compounds, anions, and metal complexes. It is also used instead of gas chromatography to analyze compounds that break down under high temperatures, as this is not suitable for a gas chromatographer analysis. HPLC, however, cannot analyze volatile compounds, as these compounds are more suited for analysis via a gas chromatographer instead, due to the nature of these molecules. The sample that is analyzed also needs to be soluble in the mobile solvent, otherwise ideal separation will not be observed. Typical samples analyzed via HPLC include pharmaceuticals, petroleum mixtures, and soil samples. The sample can be prepared using a variety of methods depending on the nature of the sample being used, the composition of the mobile and stationary phases, and the impurities present within the matrix of the sample. A solid sample must be soluble in both its solvent and its stationary phase in order for analysis to be possible. For the analysis of a pharmaceutical pill, the sample would have to be broken down into a powder via a crucible, where it can be dissolved via a solvent like methanol or acetonitrile. This aqueous mixture of the sample can then be transferred into an autosampler or injected straight into the HPLC column. No further preparation is required. An example of an alternative sample preparation method is the preparation of pesticide samples using the quick, easy, cheap, effective, rugged, safe method, or quetches. The pesticide sample is homogenized and undergoes a liquid-liquid extraction between acetonitrile and a water-magnesium sulfate mixture. The sample then undergoes a solid phase extraction where a lot of the unwanted compounds are removed from the matrix. The sample is then micro-injected at a volume dependent on the diameter of the solid phase column. This method increases the extraction efficiency of the pesticide sample. In order for the results obtained from the HPLC to be valid and reliable, there are a number of quality assurance methods that can be undertaken. The analyte peaks are usually compared to an internal standard, where a known concentration of a compound is added to the system, which provides a peak of concentration that allows for the concentration of other peaks to be calculated. Another method similar to this is doping, where a known amount of analyte is added to the sample, which creates an exaggerated peak of the sample, which allows for further quantitative analysis. The sample is usually analyzed with repeats, along with blanks being taken after each analysis. These methods allow for the results to account for interference and error, which overall increases the reliability and validity of the results obtained. By itself, HPLC does not provide much analytical information about the sample. That is why HPLC is always coupled with a detector, commonly a mass spectrometer or a UV detector. The information produced from these detectors can then be analyzed via software such as LC Solution, Lab Solution, and Origin Pro. These software packages will provide a graph of the peaks picked up by the detectors, which can then be integrated in order to find the area underneath each peak. From this peak integration, the concentration of the analytes can be calculated, which then allows for other calculations such as standard curves, height equivalent theoretical plates, and antiomeric excess. These detectors are also used to identify the compounds present within the sample via the use of an absorption spectrum and mass to charge ratios. This analysis becomes difficult when there is noise present, i.e. matrix interference, making sample preparation and quality assurance methods extremely important. HPLC/LCMS is an excellent analytical method used to separate and identify compounds. It is fast and efficient at separating and analyzing compounds without sacrificing resolution and repeatability. This is due to the method being highly automated with reliance on liquid pressure, while also being coupled with sensitive detecting techniques such as mass spectrometry. However, the application of HPLC is limited, as this method can be quite expensive and requires a high level of expertise to properly run this method of analysis. Analytical methods such as X-ray diffraction and UV-Vis IR spectrometry can be used to quantitatively analyze similar compounds as HPLC, which can be used as quality assurance to verify results, or a cheaper alternative. Thin layer chromatography is an alternative to HPLC, with the only advantage being it is easier to run while being relatively inexpensive. However, it provides little data about the sample and is less accurate and reliable, while relying on gravity and is more subject to human error and experimental error. Another alternative that is quite like HPLC is gas chromatography, which is typically used instead of HPLC for the analysis of more volatile compounds like fragrances and large hydrocarbons. However, they can analyze very similar compounds and can usually be used interchangeably.